Assalamualaikum everyone. My name is Himan Haikal. From now on, I will explain to you guys what is ODE. ODE is actually a differential equation with derivative of a function of one independent variable. ODE also called as ordinary differential equation. There are a few types of ODE. From now on, I will show to you guys a few examples of ODE. The first picture contains a first order ODE, which is the highest derivative is the first derivative. The second picture contains a second order ODE, which is the second derivative contain the highest derivative. So for now on, I will explain to you guys our problem statement. We will solving how does a resistance, which is much known as a drag, will affect the projectile motion of shuttlecock and tennis ball using ordinary differential equation. Now I will pass it to Arik for further explanation. So I want to explain to you guys about how to apply the ODE. Okay, first we need to know the initial parameters. So for both the tennis ball and the shuttlecock, the initial conditions are initial velocity, which is v0, which is equal to 30 meter per second, the angle, which is 45 degree, horizontal component, which is 30 times cos 45 degree, which is approximately 31.31 meter per second, which is the same as the vertical component. And the last is gravity, which is 9.81 meter per second, and time, which is 0. We assume it is 0. So the second is we need to know the variable and constant. So we assume that mass of tennis ball is equal to 0.057 kilogram, and the shuttlecock mass is equal to 0.005 kilogram. So the drag off, which is K, is approximately 0.002 kilogram per second for tennis ball, and 0.02 kilogram per second, which is shuttlecock. So the ratio, which is tennis ball 0.035 and the shuttlecock, which is 0.035 also. The third step of the process is the setup the ODE. So we use the first order linear ODE format, which is dv over dt plus k over m multiplied with v, which is equal to negative gravity. So we substitute the constant p, which is k per m, and q is equal to minus gravity. So we get dv over dt plus p multiplied with v is equal to q. Okay, so the step-by-step solution is step 1. We need to find the integrating factor, which is pt. So pt is equal to e with the power of p dt. So we need to integrate the pdt, so which is equal to e the power of pt. So step 2, we need to multiply the ODE by pt. So the ept multiplied with dv over dt plus p multiply with e in the power of pt and multiply it with v, which is equal to q multiply e the power of pt. So the left side of is the product rule, which is d over dt multiply with v and e the power of pt is equal to q multiply with ept. Step 3 of the process is we need to integrate both sides. So we need to integrate the both sides in the right and in the left. So we integrate d over dt multiply with vept multiply it with dt. Same for the left side, we integrate it, which is we get q e with the power of pt. Yes, so we get VE with the power of PT equal to Q over P multiply E with the power of PT plus C. So the step 4, the solution, we solve the V, which is the general solution. So we divide by E the power of PT. So we get V over T, V multiply with T, which is equal to Q over P plus C E with the power of negative PT. Okay, so we substitute P, which is equal to K over M, and Q is equal to negative gravity. So we get V multiplied with T is equal to negative mg over K plus CE with the power of negative K per M multiplied with T. So step 5, we need to apply the initial condition, which is V is equal to V0 at T is equal to 0. So we need to find V0. So V0 is equal to negative mg per K plus C multiplied with 1. So we get the solution, which is C is equal to V0 plus mg over T. So the final particle solution, we get V multiplied with T is equal to V0 plus mg per K multiplied with E with the power of negative K per M multiplied with T, and minus mg per K. So we get the final particle solution.
So based on what my friend explained just now about solving the ODE, we get the final particular solution, where we will use that solution for us to plug in the values to see how the velocity changes after 1 second. So the final particular solution is equals to V times T equals to initial velocity plus mg over K times exponential power of negative K over M times T minus mg over K. So we know T equals to 1 second because we will need to check after 1 second. So we plug in the value V times 1 equals to the initial velocity 21.21 plus 280.2 mg over K multiplied by exponential power of negative 0.035 times 1 minus 280.2. So we get the velocity for tennis ball after 1 second equals to 10.8431 meter per second. So we move to the next. For the badminton shuttlecock, we still use the same final particular solution. V times T equals to initial velocity plus mg over K times exponential power of negative K over M times T minus mg over K. So we still use T equals to 1. So we plug in V times 1 equals to 21.21 plus 2.45 multiplied by exponential power of negative 4 times 1 minus 2.45. So we get the velocity after 1 second for badminton shuttlecock equals to 2.0166 meter per second. So we can see there's much differences in the changes of the velocity after 1 second for both tennis ball and badminton shuttlecock.
So for the conclusion, there is many applications that we can apply in real life by using an ordinary differential equation, which is ODE. So in our group project, we apply the ODE in a sport which is tennis and badminton. So based on our graph, we can compare the trajectory between the tennis ball and badminton shuttlecock. So based on our graph, the dash curve represent motion in a vacuum where no air resistance acts on the object, resulting in a perfect parabolic path and the maximum horizontal range. So for the tennis ball, which is experience relatively low air resistance, follows a trajectory close to the ideal case but still shows a reduced maximum height and range. In contrast, the badminton shuttlecock experiences very high air resistance, causing it to lose speed rapidly. As a result, it reaches a much lower maximum height and lands at a much shorter horizontal distance. This demonstrates how air resistance significantly affects the motion of light object with a large surface area such as shuttlecock.